We're going to talk about the Haar system now. And Haar, of course, did his work, as I've mentioned several times, in 1909. And he led to a lot of work developing bases. And as I've also mentioned, it led in the early 1920s to Joe Walsh's work on what are now called Walsh functions. And they've been very valuable in applications for many years, but they fell in perfectly with wavelet theory. And the primordial example, I would say, of wavelet packets. And what we're going to see is for any wavelet system, we can make a wavelet packet system. And the story is that in the case of the Haar wavelet, the wavelet packet system you get on the Walsh functions. But that's a couple of lectures down the line. So now let's just go into the Haar wavelet, because there are a couple of surprises here. Which I will tell you. And so this is our function side. We're looking at the Haar wavelet. Side, the Haar function. I haven't shown its wavelet yet. And what we want to do is we're going to look at dyadic cubes. And the reason I balked when Leon asked about the motivation, but he was right. It did come from what he said, but it also came from another area. Dyadic cubes have a very nice property, a very nice geometric property, which is actually a little surprising. And that's why you have to be careful about what your factor is in front. But it's one of the reasons that the Haar wavelet works in the dyadic case. And so we're going to define the following sets. So instead of, I was going to do some things in ID, let me just stick to R, complicated enough there. We're going to let I, M, N be equal to the set of points X in R, such that 2 to the minus M n is less than or equal to x, less than 2 to the minus m, n plus 1. Okay. And the first property of these sets is a nesting property. It's the following. Proposition. So this is really a bad feature of having this being filmed. It might provide amusement to you when you're watching it, but it's very difficult not to make mistakes with the pictures here, even though I've done these calculations many times. There are certain things you just shouldn't do in public. There you go. Let I, M, N, and I, P, Q be dyadic intervals. So these are what I'm calling dyadic intervals. If the interiors of I, M, N, and I, P, Q are non-empty, then either I m n is contained in IPQ or IPQ is contained in IMN. And this is the reason I balked when Leon asked this question, because I suspect the motivation really was from what came from, it was certainly for the engineers, the motivation, because of what was going on in coding theory. But the mathematical theory, the Littlewood-Paley theory, had existed long before the work in speech processing. And basically the people doing the Littlewood-Paley theory, and then Calderon, yeah, go ahead, Calderon.
So sorry, didn't mean to cut you off. Did you mean the intersection of the interior of the intersection? I mean
the interiors are non-empty. Oh, and they have non-empty. I mean the intersection.
Yeah,
Thank you.
Yeah.
Sorry. Thank you. It's not, I can't even say it's late in the night either, so it's a non-empty intersection. Then we have that. Anyhow, the Littlewood-Paley theory, and then the subsequent work by Calderon and the Zygmunt School, they understood these things very, very well, this sort of phenomenon. And remember when I talked about a little bit about the history of wavelets, I pointed out that not only does it really go back to the lineage of the air, but it also goes back to I mentioned the work of Yaworth and Fraser. Yaworth and Fraser were dealing very, very significantly as developers of the already established Littlewood-Paley theory. And people doing things dyadically, it was a very natural thing to do in harmonic analysis from very early on. You recall, I mentioned the Lucene problem of if you have a function in L2, I mean, it was known by Kolmogorov that there exist functions in L1 of the torus whose Fourier series diverge everywhere. But the Lucene problem was given a function L2, does its Fourier series converge almost everywhere to the function itself? The answer turned out to be yes, solved in 1966 by Carlson. But initially, in order to attack that, some of the natural dyadic techniques arose, and Kolmogorov proved in the mid-20s that if you take a function in L2 of the torus, and you look at its Fourier series, but you sum over dyadic blocks, that is to say you don't sum one element at a time, but over dyadic blocks, then the series does converge almost everywhere. So this was great hope that the result might be true, but he had to use that dyadic argument. Proof is actually easy for that case. And incredibly difficult for the coefficient by coefficient. So this is sort of interesting. Let's verify.
I have a question on that.
Absolutely.
It seems pretty obvious for the example that's up on the board.
What seems obvious, Brent?
Well, first of all, the interior is just that thing without the equality on it, right? That example on the board.
Right, but now I'm saying, what if you look at, you have two of these intervals, you're saying it's obvious that if they intersect,
Okay.
they contain each other?
Okay.
Is that the way
What I was heading for is I was wondering if a dyadic interval is a more general concept, or is that the definition of a dyadic interval?
Well, so first of all, we can do it in higher dimensions.
Okay.
But in fact, that's where it's done for the Littlewood-Paley theory, but in general. But you can do it for other integers. I mean, things like that. But do you mean more general than that somehow? Or?
Well, I was just wondering what's a dyadic interval? I mean, what's it?
Well, it's the power 2 thing again.
Okay, it's dyadic. And
we're going to see how these behave, and then you can extend it in certain ways. But maybe I'm missing something about ultimate extensions. But let's deal with this. So proof. Assume that n over 2 to the m, and then n plus 1 over 2 to the m, intersection q over 2 to the p, and then q plus 1 over 2 to the p is not n. So that's what we're assuming. And to fix ideas, you can see any sort of symmetry is going to be okay here. Let me pick one case. The other cases will all be the same. So assume, without loss of generality, that n over 2 to the m is less than or equal to q over 2 to the p is less than n plus 1 over 2 to the m. Okay? Any other situation, it's going to be the same type of calculation that I give. Okay, so several cases. Case 1. And let's call this 1. Case 1, assume m is equal to p. And in that case, then n is less than or equal to q is less than n plus 1, and so that implies that q is equal to n. And so they're equal, so I've got contained. That, needless to say, is the simplest case. So, case 2, assume m is less than p. So if m is less than p, then we have that 0 is less than p minus m, and so 1 is less than or equal to p minus m, and so 2 to the p minus m is bigger or equal to 2. And so therefore, 1 implies, if I just write down my inequalities, that n over 2 to the m, and I want to write that down now because p is bigger than m with a p in the denominator. So I have a 2 to the p, and I get rid of that up high, so I have a 2 to the p minus m times n. Okay? And by my hypothesis, this is less than or equal to, this is by 1, this is less than or equal to q over 2 to the p. And that's less than or equal to by 1. Now, just by my hypothesis, that's less than or equal to n plus 1, 2 to the p minus m over 2 to the p, which of course is my n plus 1 over 2 to the m. So what that means is, therefore, since that's, oops, I have a, that's strictly less than here, that's important. And so what that means is, so therefore, q plus 1 is less than or equal to n plus 1, 2 to the p minus m. But that, because of that's, because this then is equal to this, then we're done, right? Because I have q plus 1 is less than or equal to that, I'm over 2 to the p in both cases. And because of this equality here, I can assert that therefore this implies that I PQ is contained in I MM. By the way, it'd be interesting to probably write a little computer program for this too. Show how this really works. But just arithmetically, what I just said is fine.
From a picture, it's rather clear, right? If you divide everything by
Yes,
two, right?
yeah. In fact, I'm going to draw some pictures. You're absolutely right. I'm going to draw some pictures like that for the next step up. But, I mean, the result itself has shock value to me. The fact that this dyadic thing works the way it does. And then for the third case, case 3, assume P is less than M. And once again, well, not once again, I have to consider 2 subcases. Namely, N over 2 to the M is going to be equal to Q over 2 to the P, and N over 2 to the M is going to be less than Q over 2 to the P. I probably didn't have to do that, but I was just trying to be systematic. Okay, so suppose N over 2 to the M is equal to Q over 2 to the P. Well, P is less than M, so that implies that 2, if I bring the P over the other side, I have 2 to the M minus P is bigger than or equal to 2. Which is different than we had before. We had 2 to the P minus M, bigger than or equal to 2. And so, and this implies that 1 over 2 to the M is less than or equal to 1 over 2 to the P plus 1 is less than 1 over P. Because here, if I do the 1 over business here, when I bring this over the other side, I have 2 to the M bigger than or equal to 2 to the P plus 1, and then 1 over, and there I am. This implies that 2 to the M bigger than or equal to 2 to the P plus 1, so that 1 over 2 to the M is less than or equal to 1 over 2 to the P plus 1. And this is automatic. And so thus, I'm going to look at Q plus 1 over 2 to the P, and I want to get that less than N over M, 2 to the M, N plus 1 over 2 to the M. Excuse me. I'm going to get it bigger than. That'll still give me my improvement. So this is equal to, by my hypothesis, N over 2 to the P plus, excuse me, it's equal to, Q over 2 to the P is equal to N over 2 to the M. And then 1 over 2 to the P. And this is supposed to be 2 to the P. And that's bigger than, by the way we have things here, N over 2 to the M. And 1 over 2 to the P is bigger than 1 over 2 to the M, plus 1 over 2 to the M. So that's equal to N plus 1 over 2 to the M. And so voila. So since I assume these two guys are equal, this implies that I, M, N is contained in I, P, Q. Okay? This probably be capable of putting you all to sleep doing this. But, I haven't screwed up too badly in the details. Okay. I know. No. Well, we're taking any integers. M and N can be any integers.
How about not integer?
Oh no, I'm only dealing with integers right now. And so now the final part of this case is to look at the case.
That's not true.
What's that?
When they're not integers, it's just not true.
Yeah.
They can
That's right. Okay, so now let's suppose that n over 2 to the m is less than q over 2 to the p. And we are in the case where, let's take p less than m. And in that case, I'm going to look at the distance between these 2 points. So we don't think of it as a minus. I'm going to look at the distance between these 2 points, and I'm going to have 0, d, the distance, is going to be q over 2 to the p minus n over 2 to the m. You've got to be laughing because a grown man shouldn't be doing this. Or?
No, I'm laughing at me.
Oh, I see.
Why is that equal to 0?
It's bigger than 0 net, sorry.
Oh.
And so now, because of the hypothesis there, I can bring the m down, and I have this is equal to q 2 to the m minus p minus n over 2 to the m, right? And so that's got to be equal to, everything's an integer here, since m is bigger than p, that's equal to some k over 2 to the m. K positive integer. And so therefore, n plus 1 over 2 to the m. So the distance between these two guys is like that. So therefore, n plus 1 is less than or equal to q over 2 to the p. So that distance becomes too big. That can't happen until we obtain contradiction. And so this contradicts our assumption 1. So it can't happen. Okay. Any other cases are simpler than this. I mean, we have to look at a couple of things. And I think that's worth the quad error demonstrating. More Russell. When I said to Adam, was he just laughing because a grown man's doing this? It brought back the memory of years ago. I spent a year in school in Superiore in Pisa, and one of the people there got elected to the Italian equivalent of the National Academy of Sciences. So he went down to Rome to give his address to all the members of the National Academy. And after his address, one of the members came up to him, was a very applied physicist or an engineer or something. Came up to him, and this fellow was an algebraic geometer, rather famous now, since passed away. And the engineer said to him, he said, "I didn't think grown men did that sort of thing." So we have to watch our backs, you fellow mathematicians here. Okay. So we have this, what strikes me as a surprising property if you don't think about it in depth. And now we're going to use that for the following case. Let me stay in another proposition. And what I'm writing here now, you can see that you can define this this idea for in higher dimensions too. And these results are all true in higher dimensions.
Professor, let me just kind of run something by you and tell me if I'm missing something here.
Go ahead.
I would look at this and say those things are characterized by, if you write the numbers in binary, there's, I mean, every one of those sets is characterized by some preface in binary, and then the tail is anything.
Very good, Brent. You are a sharp cookie.
And from that point, it just seems.
Yeah, but I know some people think that way more clearly than I do. I don't.
Okay.
But you're absolutely
But
right.
you can prove it that way, right?
Yeah, you're absolutely right.
Okay.
That's the way these things are done.
Okay.
No, you're 100% right. Yeah, in fact, there's a whole branch of this subject, this harmonic analysis on trees. It doesn't mean you do it when you're in a tree, but it is this doing harmonic analysis where the binary business plays a major role in how you develop these things. And that's now become a very important issue and something actually Nate's working on with us. And I'm very business because of so much work is done on the graphs. And I must say, it's not the way I was trained to think, but I'm being forced to think that way. And it's quite fascinating, doing partial differential equations on graphs and this sort of stuff. So, but anyhow, you're absolutely right. Okay, so proposition. So again, psi is a half function. Psi is a half. My recollection is, in fact, I encourage you to go look at Haas' original paper, or maybe Walsh's original paper, because they certainly started very early on by looking at binary expansions. And certainly by the time that Walsh was here, I mean, Walsh taught me potential theory at Harvard, but then he came here my first year here, upon his retirement. And that's when he told me, oh, I should go look at these old NRL books on what I call Walsh functions. And I never did at the time, but I did after he passed away. Typical Benedetto to screw up a little bit. But basically, people were definitely dealing in those terms then, in the 60s and 70s, thinking of things in binary. There's a wonderful book, 3 authors, and it's on the Walsh functions, and they have very big sections with that sort of technology. So it's I d to half function. And then at A is for all m and n, support psi mn is equal to I mn. And B, the higher wavelet system is orthonormal. And basically, for the proof, I'll skip the absolute easy parts. A is an exercise. And it's just a matter of writing down, seeing how this thing spreads up. I mean, basically, this is IMN. Psi itself is supported on 0 to 1. And then if you play the game of what IMN is, you see that it's the support of psi mn, which is psi mn is equal to 2 to the m psi 2 to the m x minus n. So that means 2m x minus n belongs to 0, 1. And this is how you do it. If and only if 2m x belongs to n plus 1, if and only if x belongs to n over 2 to the m n plus 1 over 2 to the m. Okay, so I just did it. And so that means this is the only place the half function vanishes. And so the only place psi mn, it doesn't vanish. So the only place that psi mn of x doesn't vanish is this. And that's, so the at B, let's take let m equal p and n equal q. Then the L2 norm psi mn squared, or that's just equal to psi m. Well, just equal to 1. And then because of the dilation we use, because of the factor here, this guy here, I mean, basically it's equal to 2 to the m, so I have a 2 to the m over 2. Well, I can write over 2 here, sorry, it's over 2. It's very relevant for the normalization. So this is 2 to the m, and then I'm integrating, because we just did the support thing. Where am I integrating over? I'm integrating from n over 2 to the m up to n plus 1 over 2 to the m. I'm squaring it, so it takes values plus or minus 1, so it's just 1 in here. And that's a length 1 over 2 to the m. So this is okay, and now let's prove the orthonormality. So the 2, let m equal, by the way, this I know must seem very tedious. Stay awake because we do have a punchline before I let you go to let m equal p and n not equal to 2. Then, if we look at n over 2 to the m and n plus 1 over 2. Question? Right. Slow and steady Benedetto wants to write it all down. Okay. So that intersection with n is not equal to q. So if I look at q over 2 to the m, and then q plus 1 over 2 to the m. Just pointed out, since these guys want it. And so that implies that psi m n psi eq is equal to 0. Now, let's look at the following case. And this will get that picture that Davner said earlier, but I can draw it in just a moment. Suppose m is not equal to p. Well, think of M, N, and P as fixed. If we do that, then let's look at our intersection here. When I look at my intersection, what we have is we have n over 2 to the m, n plus 1 over 2 to the m. I'm thinking of the p is fixed now too, so that's intersection q over 2 to the p, q plus 1 over 2 to the p. And so that means that if q is big enough, I've got this fixed interval. If q is big enough, or small enough going to minus infinity, it'll be empty. Right? I'm just saying something obvious, but it motivates the way I thought of writing out the details here. So this is empty for q large enough or small enough. And therefore, the inner product psi mn psi pq is 0 in this case, in these cases. Say that again?
In the second way, this intersection should be 5. Or it's not equal to 5.
The intersection is, hang on,
Not 0. Yeah.
is equal to, in these cases here, it's empty. Is that what you mean? Thank you. Okay, and okay, so if the intersection here is not empty, so if star is not empty, then we're going to use our inclusion result. It's called proposition 1. Then we'll use proposition 1 to give I, M, N contained in IPQ or IPQ contained in I, M, N. That's certainly going to be the case. How's that going to help us? I think you should give the lecture. No, you're right. So you're seeing the geometry, which is great. Let me write out the details. So that's what proposition 1 gives. And so we would complete our proof, and this is why you have to take this wavelet that's plus or minus 1. The wave goes up and down. We'll complete our proof. So suppose I, M, N is contained in IPQ. It's one or the other. So we'll be done if we show that psi PQ is constant when psi mn is not 0. Everyone see that? So that's what's going on with this. There's this halving procedure, and we really need a wavelet. something whose integral vanishes. Now, I say that because it's not always true. You don't, in the general theory, that's not, there are places where you get around that, but the intuition really is you need its integral to be zero. It's a nice L1 function. And this is the reason, basically, because of what's happening geometrically. Okay, so let's write out a little specific example of that, and then I'll prove it if I feel like. I mean, if it's not a narrative, if it's not transparent, or if I feel like I'll time it. So, I mean, this example is really the whole proof. So, for let m equal minus 1, n equals 0, p equal 1, and q equal 2. Okay, what do these sets look like then? Well, I minus 1, 0 is equal to, well, I've got n equals 0, so it's equal to 0. And then I've got n equal minus 1, so it goes up to 2. And then I1, 2 is equal to, well, n is equal to 1, and so I1, 2, and so I have, whoa, it's equal to, n is equal to 1 over, well, I'm doing the wrong one. N is equal to, let's mix my m and n. So I have 2 over 2. So it goes from 1. And then n is equal to 2, so it's 2 plus 1 is 3, divided by 2, up to 3 halves. Okay, so those are my so my sets. Now, if I look at those sets, there I am at 0, up to 1, up to 2. And if I look at psi minus 1, 0, well, psi minus 1, 0 is 2 to the minus 1 half psi of 2 to the minus 1 t, and that's it. And so in particular, this is of height 1 over the square root of 2. It goes from 0 to 2, so that means from 1 to 2 it's minus that, right? So there's psi minus 1, 0. What does psi 1, 2 look like? Well, first of all, it's in here. Support. So this is 3 halves. And so 3 halves plus 2 halves is 5 halves. Divided by 2 is 5/4. So here I am here, where it's going to split. And I'm going to go up to so this is the function psi 1, 2. And that is equal to 2 to the 1 half psi of 2 to the t minus 2. So this height here is square root of 2. And so what happens is that the function,
Just one. One.
say it.
It's the coefficient of the function would be 1 maybe. So this is 0. Then we get 0.
So where am I here? I'm looking at psi 1, 2.
Yeah. And
And psi 1, 2 lives on the interval 1 to 3 halves.
our m is 0, right? What's the coefficient in front to the minus m over 2? So that would be to the 0. Would be 1 and that. Maybe
M here is 1.
Oh
M
yeah,
is
1, 1. Sorry, yeah. Sorry, that's right.
So it's 2 to the 1 over 2.
Yeah, sorry.
So I've got two functions here. One looks like this. And the other one looks like this. And the point is that this guy living on 1 to 3 halves is on a part of psi minus 1, 0, where it's constant. So that means that the integral of psi minus 1, 0, psi 1, 2 conjugate is 0. So the idea is exactly because of this embedding business that we're going to get orthonormality because of this phenomenon. And I think that maybe that's illustrative. I worked out the details, but maybe that's illustration enough for you to, as an exercise, write it down, please, and insert it. So part 5, do this calculation generally. There's no surprises in it, just you have to do it. Did you get it? So prove part 5 of proposition 2 on the orthonormality of the Wavelet system. I think that's fair to do that. Huh? Does anyone think that's fair? I want an unbiased one. What do you think, Will? Is that fair?
Oh, yeah, fair enough.
Okay, so the real kicker is the following result. I mean, if you understand what I just did here, you'll be able to write this down. Okay, so this is the result we want to prove. Coming up now. Theorem. Let psi be the high function. Then psi mn is an orthonormal basis for L2 pi. Then psi mn is an orthonormal basis for L2 of I. So what's the strategy for proving that? Well, first of all, proof by the orthonormality, which we just did, module one general calculation, we really did it. By the orthonormality of psi mn, and a standard Hilbert space result. And that result is the following. We have a Hilbert space H, and we have En orthonormal in H. Then the span, the closed linear span of the ENs, I take the span, finite linear combinations, and I close it up. Closed linear span of the ENs is equal to H if and only if for all x in H, x is equal to sum x En En. So this is sort of basic Hilbert space theory. We'll be proved to you next week. I mean, you people have a lot of choice next week. We do more exercises, more functional analysis. But I really encourage you, just in case you haven't started the exercises, to be prepared to talk about them next week. There's nothing like that sort of thing for an impetus to start writing down solutions. But this is a basic vacuum Hilbert space theory. And it's, by the way, it's astonishing. The orthonormality buys you a lot. Because span is like nothing. It's like playing the one-armed bandit. We have no guarantee of convergence. I mean, the one-armed bandit is going to, maybe that was a bad analogy, but the way I was thinking was you get 3 different things every time. And in a span, you can take an element, and you're going to, because it's in the span, there's going to be a sequence of elements from the span that's going to converge to it. But at each step of that span, it's going to the sequence that's going to converge to it, the coefficients are all different, or could be. Whereas the decomposition is a nicely trained little lad, so it just sort of latches on. Okay, so by the orthonormality of psi and n and the standard Hilbert space result, we shall prove that the span of En equals H in the following way. And what's going on here is there's going to be 3 steps, the way I'm already found. And 2 of them are routine in the sense of if you've had some analysis. I don't mean psychiatric type. It might be easier that way too. I don't know. But one of them is it's almost counterintuitive. At least it was to me the first time I did it, because I tried to prove the result without reading, and I just went all along. So, in any case, we're going to proceed in the following way. Given epsilon bigger than 0 and G in L2 of R. So first, show that there exists an n, an integer, positive integer, and there exists Gn in L2 of R such that the support of Gn is contained in minus 2 to the n, 2 to the n, and G minus Gn in L2 norm is less than epsilon over 3. Now that is something that you know how to do. It's almost a definition of a Lebesgue integral. So if you've had a basic real analysis course, that's essentially how you define the Lebesgue integral one way to do it. So this part is if you don't know this stuff, then it might be difficult to do, but it's a sort of standard first year graduate real analysis. So we started with epsilon and a G, and now we've come up with this Gn. The second step excuse me. Second, show there exists an M in N, and there exists an F in L2 of R, such that the support of F is contained in minus 2 to the N, 2 to the N. That's virtual F. Such that the support of F is in there. F is constant on intervals of the form n over 2 to the m, n plus 1 over 2 to the m, of course that's a IMN. And Gn minus Fn in L2 norm is less than epsilon over 3. Now, this one is another exercise I want to make. This is something you can do in a computer. So I'd like to have, as an exercise, implement step 2 computation.
Exercise Z.
Oh, is that Z? Oh, thank you. There you go. Already done. Already written down.
I mean, this is also like the standard density result.
It sure is. These are the two easy parts. And here again, it's the Lebesgue integral. Basically, you can approximate step functions. You can use step functions to approximate integral functions. Okay. And then the kicker is not easy. And the third step is show there exists double sequence CMN. Well, let's do it this way. There exists CMN in C where M and N are in F1 cross F2, where Fj in Z is finite. Such that F minus the sum over all these MNs in F1 cross F2, which CMN psi MN in L2 mode is less than epsilon. So basically what we're doing is we're coming close to this function, and this function comes close to the Fn, which comes close to the excuse me, which comes close to the Gn. I made a mistake. This is an F here. Okay. So the F comes close to the Gn, which comes close to the G. 1 and 2 is observed, as I mentioned, are essentially fundamental results in Lebesgue interval. It's almost how you define the Lebesgue interval. And this, of course, says nothing about keeping the same coefficients. This really is just showing span. Getting the same coefficients at this stage would really be difficult. So all I'm really proving is span here. And that, we really do need that basic functional analysis result. I'm not, maybe there's someone else who knows how to do it better. I don't know how to do it. But on the other hand, I didn't know how to do this when I tried to prove it by myself. I actually had to read how it was done. So, I mean, a lot of things I have to read how to be done. That's not a promise, but this I thought I could do. So even though I'm cheating you a little bit, I think I'm going to stop tonight because to prove this will take a significant amount of time. And I really hope you take advantage of next week's class because, and that means prepping beforehand. Really start working on the problems. Okay? And as far as functional analysis goes, come up with any questions you have about the functional analysis. Because we're not using deep stuff in functional analysis. We are using sort of basic, very useful stuff, like the open mapping theorem, these density results. So ask questions about it. Okay? Any questions about anything?
Have we used the open mapping theorem?
Yes, you do.
I mean,
I didn't tell you. When you on the frame operator, basically you show that it's continuous, and when you show you get an exact frame.
But we haven't done that yet.
No.
Okay. I didn't notice it, and I was just wondering.
Yes.
In your statement that the frames determine an isomorphism.
The frames, that is a topological isomorphism, that's right. No, but it's a top, that's right. So this will take 1 second. It's a topological isomorphism onto that L of H, as opposed to onto all of the coefficient space. But there, and so that means that the inverse mapping is continuous, because you've got the one-to-one, you've got the onto that space, that is a Hilbert space also. And since you have continuity, then by open mapping, you've got the thing going backwards. Not important right now, I'd say, but it'll arise again. Yes, sir.
That didn't matter, but did you want this to be epsilon over 3?
Absolutely. I mean, we're on film here. And that was Abner who corrected me.